Today, class, we are going to have a very exciting lecture on power systems! Yeah. And without power systems, machines would be really boring because they would, see, so you need power systems to keep things moving. And there's a lot of really cool things in power systems for, how do you actuate drills, spring launchers, machine tools, pneumatic systems. The whole world moves because of power systems. So let's get right into it. How do you pick a motor? What do you do? Well, I go to my catalog. How? There's just so much stuff. So the first thing you want to think is take a deep breath. Think about the entire system with which you are working. You have multiple pieces you got to look at. There's the mechanical piece. That's the physical interface to the world. There is going to be the electronics, including the power electronics and the control system. That will carry the signal to the actuator, the thing that is actually going to translate, transmute, transform, take the stored energy and turn it into motion. And then there's going to be your software, your control system. It'll tell the machine how to move in what path, at what speed. Okay? So you got to have all three elements, and they all work together. I wish I had 3 arms so I could show them all working together. Okay? And this very important concept of Occam's razor must dominate always. What is the cost versus the performance? Sure, I can take my laptop and I can hook it up and make a machine go back and forth. And the cost of that will be thousands of dollars for a little machine, for example, to open and close the door to my hen house. Or you can take a little Arduino microcontroller and for $10, $15 you can do the same thing. I can't run SolidWorks with that chicken door opener, the cheap one. But I don't need to run SolidWorks with the chicken door opener control computer, so why should I use a PC by itself? Okay? Cost, you got to have this balance issue. Very, very critical. Now, between your motor, your power supply, and the thing that's going to happen, move, you almost always will have a transmission. And the reasoning for that is it's really inexpensive to make a motor go really fast. But you often need lower speed, higher torque. So for example, here is a little cordless drill. The energy is stored in the battery. The control system, brain, finger, pull trigger. Listen. What happened? It went very high speed, but low torque, lower speed, higher torque. The amount of power delivered from the motor to the tool is roughly the same. There's a bit of efficiency change due to the different gear ratios, as we talked about before, but it controls 2 different functions of the drill. So for example, and watch, so the main thing is I'm really braced myself because I don't want to, when I do this demo, to start spinning around. So your first reaction is, what? I just drew the structural loop through you, dude. There's no structural loop that goes through the ground. It goes from here, through this arm, up in this arm, down this arm into here. You can't spin around, correct. But it would be pretty funny if I did. And that was the drill, not me. So see, I'm over to overpower the drill. Now, in all fairness, this had in it what's called a slip clutch. If you put too much torque, it'll stop. Now we're going to crank it to drill. Let's see if I can do that again. Ah! Ha! Now, if I put it on high torque, low speed, step 2, remove skin from hand. I can't do it. Much, much more torque. Different function. If you take a little small diameter drill bit and you try to drill with low speed, high torque, you won't drill it nearly as well as when you're on high speed. Now that's into the theory of cutting tools, et cetera, et cetera, et cetera, et cetera. That goes with understanding the functional requirements of your machine and what it's supposed to do. And in the end, the transmission will be the thing that goes from a standardized, very efficient, very high speed, low torque electric motor, for example, to give you the speed and torque output you want. This is a very important part of the systems engineering part of the problem, because when you pick a transmission ratio, there is actually some very nice theory that's explained in the text that is what gets you the transmission ratio to minimize the amount of power required to get up to speed, then the power to zoom along, and the power to come down. In other words, it'll minimize the amount of energy it takes to move from one point to another. Now, let's assume you have a car that's here, a little vehicle or shuttle on a machine. You go from here to here. How do you do it? Normally, you speed up and you come to some speed and you move across at a constant velocity, for example, where you're doing your process of cutting or whatever your machine is doing, and then you have a time to slow down. How much energy does it take as a function of the mass of the vehicle to do this total move? How much energy does it take as a function of this time to move? How much energy do I need to expend? When I look at the power to move and the energy to move, the power is something that you'll have instantaneously at any point in time as I'm going along. So you can imagine here, as the velocity is increasing, force equals mass times acceleration. So at a constant acceleration, the velocity is increasing, right? So in this first part here, where we have F equals mass times acceleration, power equals, it's often sometimes written like a little paragraph saying, equals the force times the velocity. So that is going to equal the mass times acceleration times velocity is the power. Acceleration is velocity divided by time. And see, we have to use calculus to do the details, but we can look at the expressions. Equals mass times velocity over time. This would be the maximum velocity. And here the velocity starts low and gets higher and higher. So at the peak here, this would also be BV max. And we also know up here velocity equals acceleration times time, remember? So this would be the constant acceleration term. So this goes like mass times velocity squared over time. In other words, if you tell me that you want to get to some peak velocity or transit velocity in some fixed amount of time, the power I'm going to need will go with the square of the velocity. Now, if you also look at the fact that the distance you move equals the peak velocity, right, times the time over 2. Because remember, if you're going along at some velocity here, the area under this curve, when I get to the end here, the total area in this curve equals the distance traveled, time, velocity. So the velocity is this peak velocity times the time over 2 is the area under this triangle. That will be the total distance I traveled, right? So the velocity, this is or max or peak, let me use the same terminology, goes like 2 times the distance divided by the time. So your power to move goes like mass 2x over t squared over t. Or your power to move goes like the mass times the velocity squared, 2 times that, over time cubed. This is perhaps the most important part of this entire lecture, talk, hang out and do power-based systems together. This. Because, oh boy, that was a really cool machine. You know what? Let's make it go twice as fast, dude. No problem. Yeah, we'll just crank up the power. If you want something to move in half the time, you need 8 times the power. So when you look at these car ads, 0 to 60 in 4.2 seconds. Yeah. And the next one says 0 to 60 in 3.9 seconds. Yeah. You think, what? That's not very much faster. That's only 10% faster. Well, how much more power is that? If a car can go 4.2 seconds versus 3.9 seconds, so the faster car over the slower car, the ratio of the power of the two will go something like this, cubed. So you all work that out. How much more power, just sheer raw power, does the faster car have than the slower car? It's actually a very substantial number. So you need, and the distance squared is also important. Okay? This is what we mean by systems engineering, and particularly for power systems, very, very sensitive variables that you have to be really, really careful of when you make these, I don't want to say arbitrary decisions or let's do it. You've got to think in the context of what are the ramifications that are involved. And when you start putting in, for example, 8 times the power in, for example, a set of gears that's the same size, will you strip all the teeth off? Now, some people ask me when I was a kid, you know, what did I like to do? And sometimes, you know, how did you get to become a professor? Well, the reason is I used to do hot rods as a kid. And as a result, I had no money for drugs. Because we would do things like supercharge up the engine, and blow out the rear end of the car. Oh, bummer, man. You have to go fix it. Okay? So we didn't know anything as kids in terms of the math. We experimented and had a lot of fun. We wrecked a lot of parts. So there was some learning in that, but it's more fun to learn by doing the math than building it and checking it. Okay? So very, very critical. I think we've really powered that one home. So the next thing that relates to this is, okay, you figured out just the amount of power you're going to need. How do you get it there? And should you have an engine or a motor that goes 10,000 RPM and gives you 100 RPM output, or 20,000 RPM for your 100 RPM output? What is the best? And very importantly, that leads to the question of, if the output is going to be 100 RPM, and the input may go from 10,000 or 20,000 depending on the engine or the motor you pick, you need a different size transmission ratio. And the question then becomes, what is the optimal transmission ratio? Now what we mean by optimal is, what is the best way to take as much of the power of the motor as possible and put it into the output? And you say, what? What do you mean, put it in the output? Well, we have 2 scenarios. Great big infinite cosmic power motor! Itty little bitty output shaft and some magic transmission. Okay? Small little motor, transmission, infinite large output! So these are 2 extremes, in case you didn't notice. And a more realistic scenario is, now that we've driven that point home, here's your transmission output. Let's say this is the big giant spinny thing you got to spin. Or do I take a smaller, very high-speed motor and some other kind of transmission, also in the same size, big output spinny thing? Where, for example, this is some transmission ratio 10, some transmission ratio 100, and this thing here goes 10,000 RPM, and this thing here only goes 1,000 RPM. Okay? And some torque level, let's say the torque equals 100 Newton meters. And down here, need a little longer motor, the torque is 10 Newton meters. And the output here is this 100 RPM we were talking about. 100 RPM. And the torque would be 100 times that. What's 100 times 10? 1,000 Newton meters. And what is the feel of 1,000 Newton meters? Well, my mass is about 75 kilos. 75 kilos. Which is around 750 newtons. So if I take on my truck when I get a flat, and I've got to get the, so I put the, what's called the breaker bar, the socket, the breaker bar, and a long pipe out about that long, and I stand on the end, that'll generate about 1,000 Newton meters of torque. So me standing on the end of a lever arm about 1.2 meters long gives you that 1,000 Newton meters of torque. So this is a pretty severe load. So which one do I do? Which one will cost me less? You see, the math actually works out very nicely. You start with understanding what is the inertia of your load. So go back and review your basic intro to physics about what the inertia is. But the inertia is, the rotary inertia is an analogous just to the mass. And it'll have units of meters squared, kilogram meters squareds. Okay? Of the units here. What we're saying here is, if you have a little motor that goes really fast, you spend so much oomph spinning up your motor that there's very little oomph left to spin up your mass. If you've got this great big motor, high torque, lower speed motor, where you're spinning, all the effort's going into here, well, this has such a large inertia, it's not getting up to speed in accordance with the load either. So it turns out that when you pick a motor, it'll have some inertia, and the inertia of the load is what is given. And that will result in speed of the motor equals speed of the load times the square root of the inertia of the load divided by the inertia of the motor. And that gives you your transmission ratio, your optimal transmission ratio. And what it's saying is I'm going to put as much energy, as much power into rotating the motor to get it up to speed as I am going to put in power into the load to get it up to speed. And the reason I'm going to use equal amounts of power to get the motor and the load both up to speed is because the transmission ratio connects the two, so they darn well are going to have to get up to speed at the same time. And if you put too much power in the motor or too much power in the load, one is going to drag the other, and they're a team that's got to start working together at once. That's what the optimal transmission ratio gives you. So when you go to pick the motor and the load and the gearbox, they all have to work in harmony. You can start by picking a motor. Well, you have your load and see what transmission ratio that gives you. And then you can go the other end of the extreme on the higher end of speed of the motor, lower torque. What kind of transmission ratio is required then to drive your load? And what will happen is you'll find is that sometimes you'll get very unreasonable transmission ratios that are unobtainable, like 100 billion to 1. Very bad. So then once you get your workable scenarios, you then go back and you look at the cost, the physical cost of the items when you order them from the catalog, and you then minimize about the cost. Okay? So that's the logic and the rationale behind how we're going to take from the power source an appropriate transmission and get to the output load. It can be a rotary motion gearbox. The same type of analysis works for this is a transmission. Remember, for a screw, there is a transmission ratio of 1 rotation equals 1 lead's worth of motion in translation. So everything we talk about for rotary motion, there's an analogy for rotary to linear motion.